Now, I will show you, once you have done this with your ruler, you can now apply this knowledge on a way more interesting system, and that is the hoop. We'll take the hula hoop, and we're going to do the same thing for the hula hoop. And the system, the approach, will be exactly identical. We have a pin through the hula hoop. This is the hula hoop. This is point P. This is the center of mass. I call it C. It's now like this. A little later, the center of mass will be here, and this angle will be theta. The mass of the hula hoop is m, and it has a radius r. I know there will be forces through that point P, but I couldn't care less about them. All I worry about is this mg and this position vector rp. And the whole thing goes parallel. I'm going to get that the torque about that point P equals mg, and I'll fill in for this immediately the radius r times the sine of theta. And that must be equal minus the moment of inertia about point P times theta double dot. What is the moment of inertia about point P? Well, that is the moment of inertia of rotation about the center of mass plus mr squared. That's the parallel axis theorem. And the moment of inertia for rotation about this axis is clearly mr squared, because all the mass is distributed at the circumference at distance r. So it is a summation of all the masses times the radius squared. So this is going to be mr squared plus mr squared. So that is 2mr squared. So we bring this to one side. So we're going to get theta double dot plus mgr. We make this theta, small angle approximation, divided by IP equals 0. Simple harmonic oscillation in theta with exactly that same solution. But now we get, as a period, we get 2 pi times the square root of IP divided by mgr. But IP is 2mr squared. You see, IP divided by mg, not b, but now we have mgr divided by mgr. And that is 2 pi times the square root of 2r over g. And that is a cute result. Because if I had a pendulum, and the pendulum had a length L, which is 2r, and I put all the mass at the end of the pendulum, and the string has no mass, I would have found exactly the same result. Remember, the period of a pendulum is 2 pi times the square root of L over g. Notice again, there is no mass in there. It's only a matter of geometry. Geometry is the only thing that determines the period of oscillation. That's always the case. Whereas a pendulum, a simple pendulum with a mass at the end, is also, the period is independent of the mass. Not with springs, but always with gravity. So the first thing I want to show you is that if I have here an apple on a string, and to the center of the apple is about the same, to here, to this pin, is about the same distance as the diameter of the hula hoop, that they probably have very closely the same period. You see, they track each other quite well. Not precisely, because I was not able to get the lengths exactly right, but very closely. So already you see that indeed that result makes sense, but now I want to go one step further. I want to do a quantitative measurement, because I know the radius of this hula hoop. The radius, I think, is 40 centimeters, and we know that to an accuracy of about half a centimeter. So R is 40.0 plus or minus 0.5 centimeters. You will say, boy, can you not measure that any better? I mean, half a centimeter, it's almost yay big, half a centimeter. Well, the reason is it's not a perfect circle. So if you measure the diameter at various places, you don't always get the same. And so that's why I allow for half a centimeter uncertainty. So that's a 1% uncertainty in R, 1%. Under the square root, that becomes half a percent. And so the prediction then would be, if I put in the numbers here that we have, is 1.795. And that would become a half a percent uncertainty. Half of 179 is about 1. So let's make it easy, 0.01 seconds. That is my prediction. And I'm going to make 10 oscillations, which gives me an uncertainty of 0.1 seconds in 10 oscillations. So that gives me an uncertainty of 0.01 in 1 oscillation. Imagine that you come home with Thanksgiving, and you show this to your parents, and you say, oh, by the way, Dad and Mom, would you be able to calculate the period of this oscillation? I mean, they would turn pale, green, purple, and you take out your pocket, and you just do it like that. Simple. And not only that, but you can do a demonstration. You can show it to them. They'll be proud of you. Okay. Let's try it. There we go. Small angle, this is about 5 degrees, 7 degrees. Doesn't make that much difference, as long as you don't get much above 10. I don't like the wiggle. I'll start it when it stops here. No! 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Holy smoke! Look at that! 1807. 1807. If I divide that by 10, then I get 1.807. Let's call it 1 plus or minus 0.01. And if you take this error into account and this, well, you can make it a 0.7. Pretty impressive.